All right, we're going to turn our attention to something a little more interesting than a polynomial function. This is example 3 on page 168. The author has his solution there. I encourage you to look at that too for any kind of background. Also, he provides some pretty good graphs too. All right, here we go again. Find the extrema of this function on this closed interval. This is A, this is B. Got it. All right, I want you to just kind of notice this exponent right here. It's not an integer. It's a 2/3 power. That provides an interesting situation on our graph. But I do want to mention right now, if you think about this equation, this function, that any x, I can replace in any x here, any number for x that I want to, and I'm going to get an output. So I guess my point here is that the domain of this function is all real numbers, that this graph will go across my entire screen. The domain is, like I said, all real numbers. But I just want to look at a piece of it on this closed interval. So again, I encourage you, type this into y1, x min, -1, x max, 3. Okay, and when I did that, on my calculator screen, this was the graph that appeared. So I said this was -1, and this was about 3 right here. And I think my window setting for y was -5 to 5. Okay, so my graph came up like this. I have this kind of shape to it, kind of bend to it. Okay, and it does touch at the origin. And if you think about that for just a minute, if x is 0 here and here, then my output is 0. And then what happened was, then it dipped below. It dipped below in this kind of sharp corner right here. Not very much, but it did dip below. And it appeared that it came back up and it had an x-intercept of 3. Okay? I don't know if the exact x-intercept is 3. I could verify it by evaluating the function at 3. But this is kind of the graph that appeared on my screen. Okay? And for our purposes, like I said, we're just looking for a visual of where do we think the min and the max are. All right, well, the absolute min and max. So, all right, to me it appears that this left endpoint would be your lowest y value. Okay, and it appears like it's -5, but I don't know. Okay, that appears to be my absolute min. Whereas when you follow the graph, it looks like my absolute maximum may be 0. I think the lowest y is -5, and I think the highest y is 0. My work should support that. So let's come over here and find the derivative. Applying the power rule here to this term, it looks like I'm going to get 2x to the -1/3. Okay, so again, the first thing we're going to do is find critical numbers. Critical numbers are where your first derivative is equal to 0 or does not exist. So I guess in this case, I might first rewrite this derivative. It's a little different than the previous two derivatives. I'm going to have 2 minus 2 over the cube root of x. Yeah, so when I rewrite it this way, I'm hoping that you now see that since x is in the denominator of my derivative, that this derivative will not exist at 0. So what I'm looking at is saying, well, f prime of 0 does not exist. And how did I get that? Well, I just mentally figured out that I can't divide by 0, and if x is 0, then that would cause me to have an undefined situation. So, look back over here at the graph. Look at x equals 0. It's a sharp turn. The derivative does not exist at a sharp turn. So we're using the graph to help us understand what's going on here. So the equation gives x equals 0, c equals 0, as a critical number. So, because the does not exist sharp corner. Let's move on and find out where f prime equals 0. Okay, so now I'm going to return to the derivative and set it equal to 0 to find those critical numbers. Okay, here's some algebra. Myself personally, I'm just going to move one of the terms over, which happens to be this term because I'm subtracting it. I'm going to make it positive. And I'm going to set it equal to the 2 that's here. And I'll just make it 2 over 1. Okay, so now to solve this equation for 0, I'm going to do cross products. I can divide out the 2 if I wanted to, but I see that I can go ahead and do cross product. So I have 2 times the cube root of x equals 2. Divide both sides by 2. So it looks like I'm going to have the cube root of x equals 1. All right, to solve that, cube both sides, raise both sides to the third power, and that's convenient. So x equals 1. All right, so what does that tell us? I'm just using notation. It tells us that the derivative at 1 is equal to 0. This is x equals 1 is a critical number, and x equals 0 is a critical number right here. So these are 2 statements that tell us that we have critical numbers at c equals 0 and c equals 1. Okay, so let's come over here and look at the visual. Okay, at 1, all right, I know the slope is 0 because it's a minimum there. So I'm looking for highs and lows, and the only places that I might have highs and lows is at endpoints or where the slope is 0 or does not exist. All right, let's create our t-chart. All right, so what belongs in our t-chart? Critical numbers and endpoints. So we've got 0 and 1. And then going back to your endpoints, A and B, -1 and 3. Okay, notice 2 is not here. Some of the numbers between -1 and 3 are not here. Do I always have to have integers? No. These particular functions that I'm working with just happen to have nice numbers. Okay, but do double check to make sure that all of these numbers right here, these x values, fall in the closed interval. And I believe they do. All right, so come over here and show the notation f of 0, f of 1, etc. So evaluate the original equation at each of these. So f of 1 is -1. F of 0 is 0. F of -1 is -5. And f evaluated at 3 on your calculator is -0.24025. All right, so the least of these numbers is -5. That confirms with what I saw here. So I have an absolute min at y equals -5. And I'm going to continue and say when x equals -1. Absolute max at y equals, remember, an extreme value meaning y value is the y coordinate. All these are negative, so I guess I have to choose 0. So the absolute max is at y equals 0 when x equals 0. So those are your extrema right there. So when they say extrema, you're looking for, unless they specifically say a min or a max, you're looking for both. And it requires this process right here. Okay, so here's our high y and our low y. All right, I do want to look at one more example with you guys, and this is going to be one that involves a trig function. So let's spend a little time looking at this one. If you did type this into your calculator, you would see that this is a continuous curve. Okay, you can draw it without lifting your pencil. There's no breaks. There's no sharp turns. You're familiar with trig functions. Okay, so let me draw a graph of what that looks like over here on the interval, the closed interval from 0 to 2 pi. All right, just if you want to follow along again, type into y1, x min, x max. My setting is from a -5 to 5 window. Again, it's a trig function, so make sure that you're in radian mode if you're going to try and duplicate this graph. All right, the graph starts right here somewhere on the y-axis below 0. It peaks here. Ooh, that's not going to be good. It falls here. It falls below the x-axis. It starts to come, not good. Starts to come back up, comes back down, goes back up. It probably comes back above, but I think this is 2 pi right here. So that's when it comes off my screen. I encourage you guys to type it on your calculator. This y value and this y value right here are at the same location, and these y values are less than this y value. So you might want to use your calculator to kind of produce that graph. Okay, I can clearly see the maximum occurs at an interior point inside A and B. I clearly see that the minimum occurs twice. Actually, I hit the low y value twice at interior points. So neither endpoint would be an extrema in this case. All right, find the extrema, absolute min and max of this function on that interval. Derivative first. And we're noticing that this function exists everywhere. Okay, let's find the derivative. Term by term, 2 cosine x, okay, minus, okay, chain rule. Cosine's derivative is negative sine, so I'm going to put sine down, and because I have negative sine, I'm going to make this plus. Okay, oops. Outside function is sine. Leave the inside function alone. My bad. 2x times the derivative of the inside function, or times 2. And remember, we're going to probably put that up there, just so we remember not to double this angle. All right, so at this point, here's our work. Where does this derivative not exist? Well, unlike this problem up here, okay, which we didn't want to divide by 0, this derivative will exist everywhere, like in example 1 and 2. Every x is going to work here. So our only other task to find a critical number is to find out where the derivative equals 0. So set the derivative equal to 0 and solve it. Well, I can tell you this would not be something that I would expect you to be able to solve. So what I'm going to do is I'm going to say to you, let me just give you these x values, these critical numbers. Okay? This would not be an expectation for you to have to solve this without a calculator. Okay? They would give you would be given easier problems, myself included. I might give you 2 cosine x equals 0 and not both of these. Okay? All right, so let me just say this right here, that if you were to type this into y1 and find where you have x-intercepts, you will have found the critical numbers. And in doing so, here are the critical numbers. Okay. The critical numbers are pi over 2, and I'm looking for, remember, critical numbers that fall in the closed interval. I don't care about what happens outside of it. Come back, pi. Okay, 3 pi over 2 is another critical number. 7 pi over 6 is within 1 revolution of the unit circle, and 11 pi over 6. And come back, fraction bar. Okay, so those are the critical numbers. Okay, and again, I could have that notation f prime of pi over 2 equals 0. Okay, f prime of 3 pi over 2 equals 0, etc. Okay, go to the t-chart. And then, of course, we're going to have 0 and 2 pi. But we should know, based on our visual here, that at 0 and at 2 pi, neither one of those y values occurring at those x's will give us our absolute extrema. Okay. All right, let's take a look at all the y values that result by taking time to plug in pi over 2 here and here. Okay, a lot of unit circle work. So I've gone ahead and evaluated all these critical, or at least the critical numbers and the endpoints, all these x values in the original function. So when I plug in pi over 2, and pi over 2 appears to be about right here, it should be a high y value. It's actually going to be 3. When you plug in, I believe this is 3 pi over 2. Everywhere you plug 3 pi over 2 into and perform the correct calculation, you're going to get -1. So 3 pi over 2 appears to be about right here, and that makes sense. Maybe that's -1. 7 pi over 6, when evaluated here and here in the original, gives -1.5. Well, I want you to think about 7 pi over 6. Well, 7 pi over 6 is on the unit circle before 3 pi over 2. So if this is 3 pi over 2 and it's -1, then 7 pi over 6 on the x-axis would be about right here, and it appears that that value would be about -1. 11 pi over 6 on the unit circle happens after 3 pi over 2, and its y value is -1.5 as well. So it appears that right here and right here, those y values are -1 at 7 pi over 6 and 11 pi over 6. When you plug in 0, when you think about it, 0 here, that's going to be -1. Makes sense. It's not quite as low as these y values. And 2 pi, actually the graph doesn't even come back up. At 2 pi, we also get -1. So from here, we're just studying these y values and we can report our answer. We have an absolute min at y equals -1.5. Now what's interesting here that we haven't seen yet is that we have two x values at which this occurs. When x equals 7 pi over 6 and 11 pi over 6. Then if it occurs multiple times, you really should report multiple times. That's why oftentimes they just ask for the y value, because this may occur, you know, many times, multiple times. So we have an absolute max at y equals 3 when x equals pi over 2. So those are extreme values. All right, so we have guidelines to help us do that. So I tried to look at, you know, a case of an interesting case for each of these problems and kind of build on what we did. So we'll see how we do.